And actually, Ola, I might ask you to comment a little bit on this survey.
Oh, I thought that. Yeah, this was one I put in, so that was unfair. Yeah, and that touches on one of the questions or one of the comments that was raised from the survey, because calibration is. There were two different answers. One was that calibration is normalizing the output of a turbidity sensor to some turbidity standard, for example, 100 NTU. But there is no turbidity standard that exists for acoustics. That's really important to realize. So there's nothing really to standardize against except actual particle concentrations. You can't go out and buy an NTU standard and use it for acoustics simply because a turbidity standard is very fine particles and it's designed for optics. When you make something like an ABS, you have to come up with your own, essentially.
Yes, and certainly turbidity sensors have the advantage that it's not that difficult to make a stable standard. You can make it from very fine particles that don't settle and so on. For people who are accustomed to using turbidity standards, it's a bit of a mental adjustment to have to think about the ABS and how it's sensitive to larger particles. So this is just a photo on the left side of our setup that we use for production testing in the lab. So we have a tank that we've made specially for this that has baffles and a stirrer and arrangements for mounting the sensors in the right orientation and so on. And we have some special software that's used for collecting the output.
Yeah, I just want to reiterate that what we're doing here is we're using the flat part of the curve here.
Right.
The ABS. So this is where we actually do the calibration.
Yeah, exactly. We go through a process. You can see we do 6 of these at a time. And it is rather labor intensive, actually. Found that this is a number that's manageable to do at one time. If you try to do more, then the mixing becomes more of a challenge. We basically do 2 major calibrations on these units. Number 1 is just measuring the sensitivity of the response versus concentration. All of our measurements with these instruments in the lab are done using these glass particles, Ballatini particles, 75 to 90 micron glass spheres. These are particles that are actually manufactured for the purpose of bead blasting and polishing things. What we do is we wet sieve them and so on to make sure that we've got particles just within that 75 to 90 micron range. We do a test at room temperature with the different concentrations that you see listed there, ranging from 1 milligram per liter, which is a very small number of particles actually, up to 1 gram or 10 grams per liter, 10,000 milligrams per liter. The electronic response of the ABS is not perfectly linear. Like any ultrasound receiver, it's got some nonlinearities inherent in the circuitry. But we correct for all that by simply making a lookup table with these 6 reference calibrations in it, reference concentrations, and interpolating between the measured concentrations. And that's enough to give us quite good conformity with the response, an effective linear response. I will say that at 1 milligram per liter, the number of particles involved in that, especially the number that are passing through the sensitive range at any given moment, is small. At the low end of the concentration range, the data are inherently noisy just because of the physical characteristics of the measurement. So we typically state that 1 milligram per liter is the low end of the measurement range. Also keep in mind that these particles that we use are near are the ones that are at the peak of the sensitivity of the instrument. So if your particles are smaller, you would not probably be able to measure down to that 1 milligram per liter range. The plots that were shown earlier in the presentation that showed 5 to 10 milligram particles, those are quite small for the ABS. Those curves would be shifted lower than what we get from this standard calibration with the 75 to 90 microns. Then the second major step in our calibration is to measure the temperature sensitivity. The electronics are quite stable with temperature, but the transducer itself is somewhat sensitive to temperature. It can be pretty significant, and it does vary a lot from unit to unit. So it is something that has to be measured individually for each ABS. We do that temperature calibration in essentially the same setup that you see in this photo, but we chill the water, and so we start out with typically around 5 degrees C, or maybe a few degrees lower if we can. We put in a constant 1 gram per liter concentration of the same particles, and we measure how the response changes over the whole range up to about 35 degrees C. I remark there this is slow because we're heating a not insignificant amount of water, and also because it does take time for the instrument itself to track the temperature of the water. So that it's a process that takes at least a few hours. Again, we do that on batches of 6 instruments at a time. The results of the temperature calibration are fitted to a polynomial, usually a second order polynomial. When the instrument is deployed in the field, it has all this, it has the lookup table, and it has the polynomial coefficients for the temperature calibration in its memory. And it applies those in real time when it makes its measurements. We get a lot of questions from users, again, who are accustomed to calibrating their optical or their turbidity sensors. And they want to know how to get the most accurate data with their ABS. The fact is, it's hard. To make a measurement using these larger particles, they do settle quite rapidly. And it took us quite a bit of experimentation to settle on a combination of mixing, the vessel geometry, how rapidly we mix, and so on. It took a lot of trial and error to come up with a stable setup that we can use in the lab. I advise most people that it's probably not going to be worth their trouble to duplicate that effort themselves. And I encourage them to actually use in situ data for calibration. Now, of course, the in situ calibration is not simple either. It has its own challenges, and it requires some expertise to do it properly. We consider it best that you have the instrument at your field site in situ, so that it is measuring real particles in a real situation, and that you take bottle samples as high quality as you can, as close as possible to the actual site. Because as you probably all know, the distribution of these larger particles is not going to be uniform within a river or whatever other body of water. It's going to be sensitive to currents and all these other things. And it's going to be more sensitive to those factors than a turbidity measurement. There are weaknesses and compromises and costs in each approach. Basing your calibration on field samples is likely to give you the best, most reliable answers. Pitfalls and concerns. Any of you who have tried handling larger suspended particles in the lab know that it is challenging to get them properly mixed. In our particular setup, we've worked out standards that give us repeatable results. There's kind of a delicate balance, actually, between mixing speed sufficient to keep things suspended versus introducing bubbles. Bubbles definitely will affect the reading. They tend to depress the readings because the bubbles, at least if bubbles are clinging to the instrument, as they are in this picture that's shown on this slide, they tend to diffuse the signal coming from the transducer, and they tend to make it weaker. So they depress the apparent concentration. So when we are mixing in the lab, we have to be constantly vigilant about bubbles. It's not necessarily possible to avoid them completely. So we need to, we have a little wiping fixture, which it's shown in the picture, but it's kind of hard to see. Kind of a star-shaped wiper that lets us wipe the surfaces of all the sensors while we're in the process of measurement. And also, when we measure those high concentrations up to 10 grams per liter, you can't see the bubbles with your eye anymore because there's so much optical diffusion. So when you get up to the higher concentrations, we actually have to temporarily stop the mixing, let the particles settle out so that we can inspect, look for bubbles, wipe them off, and then we can resuspend everything and resume the mixing. Flocculation can be a concern. We haven't run into that in our lab situation much. These particles we're using and the spans of time over which we're using them, they don't seem prone to flocculation. But we have definitely had customers, one of our early customers actually, who had done some lab experiments, and he was using samples he collected from a river. This was in South Africa, actually. He'd collected them from a river. He found that over spans of even as little as a few hours, that the readings gradually decreased. We eventually concluded that it was due to flocculation in his natural samples that was happening over those time scales. For any sort of prolonged experiment, or if you're not sure if your samples perhaps have been sitting in a bottle somewhere and flocculating, it is definitely something that you need to consider. Yes, as I mentioned, bubbles. You definitely have to remain vigilant about bubbles throughout any sort of experiment like this. This just shows the picture of the instrument, and it does not include the Y cable that we'll be discussing. This shows the smaller tank. I should have put that plot back in here that shows the ABS curve and the OBS curve, but it's probably burned into your memories by now. So as you recall, the OBS sensitivity goes down as a function of increasing particle size, and the ABS has sort of an opposite characteristic. There's a crossover point where there's an optimum particle size for measuring this pairing coefficient. And that particle size is about 30 microns. The difference between the 30 micron particles and the 75 to 90 microns that we use for the other calibrations, having smaller particles helps quite a bit in terms of being able to keep them suspended. And also the fact that this pairing process doesn't require a precisely known concentration, because we're only looking at the relative response of the ABS and the OBS. The AOBS calibration is something that happens after the ABS has been completely calibrated through the process I described earlier. And then we put in a turbidity sensor and the ABS together with these 30 micron particles. We're using Arizona test dust that's sieved in the 20 to 40, I believe, 20 to 40 micron range. So its median is 30. We do this because it's not a very long, complicated process. We usually do this one pair at a time in this smaller tank. This is just a small cylindrical vessel that has some vertical baffles you may be able to see on the photo to help with the mixing. Although, as I say, it is easier than using the big tank and the big particles, it does still require care to make sure you've got enough stirring velocity to get your turbulence up. It so happens that the particular unit stirring plate that I used for this picture is not one of our better ones for this, but it was good for the picture. We had to try a few different ones in the lab to find one that gave us enough stirring power to get this job done. it's fairly easy to judge whether the stirring is proper by changing the height, or the depth, I should say, of the sensors in the water. The ABS does not see the bottom of the tank until you get within 10 centimeters. So you can move this up and down a little bit in depth and see whether that's correlated to the readings. And if it is not, then you have achieved good mixing. The turbidity sensor has an analog output in the case of the ones that we package in the AOBS. It has a certain offset in clean water. So we first measure the clean water offset. Then we put in a moderate concentration of the particles, typically it's a few grams per liter. All we need to do at that point is measure what is the average output from each of the units. It's the ratio of the ABS output to the offset adjusted OBS output is our pairing factor. Pretty much the same considerations, precautions go into this as into the ABS calibration. In a lot of ways, this is an easier thing for most users. It doesn't require quite as much fiddling around, quite as much optimization and careful measurement as the basic particle calibration of the ABS does. So it is something that we tell users, yes, you can probably do this as long as you're careful in the lab and use the right particles. Same considerations, mixing, but as I keep saying, it is noticeably easier for these smaller particles than it is for the 75 to 90. There is once we've sent a few of these out into the field and we've gotten a little bit of feedback from customers, the particular OBS that we're pairing is not it's not highly sensitive. You can choose different OBSs that have different degrees of sensitivity. The one that we use, the Turbidity Plus, at least on its standard sensitivity range, is not a super sensitive OBS because we wanted to make sure that it would never saturate within the range that's measured by the ABS. What that all means is that the offset drift in the OBS, once you multiply it by the pairing factor, can turn into something on the order of milligrams, a few milligrams per liter. And so it is possible that the offset drift can give you negative a few milligrams per liter readings. And, nobody likes to see negative turbidities. But the only thing to keep in mind there is that is the low end of the measurement range of this instrument combination. So if you do need if you need a highly sensitive measurement of low concentrations, this isn't the ideal instrument. This is designed to be hardy and to tolerate a wide range, including especially the upper range that you might find in rivers. Yes, there are approximations. The exact size of the particles makes a difference. Imperfections in the individual OBS and ABS, those are all there. And it's certainly, this is not a measurement that comparable to measuring rubidium time standard or something like that. We don't have many digits of precision here. It's something measuring a kind of chaotic and noisy natural measurement. So, and it's unquestionably superior to the alternatives that we have for making this measurement.